through for the next hour and a half or so and talk about RF, how RF works, how we build networks with it, and kind of some basics of channel planning and building networks with wireless links. I've got a bunch of slides on that. I think we will skip around in them a little bit because there's probably more than we can or need to cover in the next hour and a half. Then we've got some hands-on stuff where we're going to build our network here, get our Barbie internet service, and then practice with some cable crimping and some hands-on stuff, see how that works, and move from there. So cool. Okay, so jumping right in then, let's talk a little bit about RF. So RF comes in, like we mentioned earlier, Althea networks don't have to be wireless networks. There's no requirement or probably even really recommendation that they necessarily be wireless networks, other than just that in a lot of cases that's the easiest and fastest way to get started. With a wired network, you have to start tearing up streets and laying cable and doing all of that. That's expensive and difficult and not what most of us are probably going to be doing immediately. So building a wireless network is the fastest way to get started, get building a network, expand into communities, and be able to provide service. So with that in mind, we'll talk about some of how that works and how we build these networks. I guess just to kind of get started, this is a little wireless radio. There's another one at the back of the room there. If you're not familiar with these are made by a company called Ubiquiti, and they are primarily for building this type of network. They're used in a lot of different ways, but one of their primary uses is to build wireless internet networks. The idea for these is that you point these two devices right at each other, and then you get a connection between them that could, in theory, have something like a few hundred megabits of throughput.
What is the device called?
This particular model is a nano beam. There's Ubiquiti makes a lot of different devices with a lot of different model names that I can't ever really remember. But what's that? You got it? Okay, there you go. I'm going to rely on you. I know a lot of them, but they have a lot. But their most recent product line is based on 5 AC Wi-Fi, so it's 5 gigahertz stuff based on AC Wi-Fi and then Ubiquiti has some of their own tweaks. So if you're using all Ubiquiti equipment, you can use some of their kind of enhancements to the protocol to make the devices work a little bit better with each other, although they are backwards compatible with Wi-Fi. So you could, in theory, connect a regular Wi-Fi device of any kind up to one of these. It just wouldn't have all of the kind of extra Ubiquiti specific enhancements. In this situation where we have one device pointing at one device like this, we call this a point-to-point connection. These devices are only talking to each other. So this is, I could have my internet connection here, and I could have a customer over there. But there's also this situation where you have a point-to-multipoint connection. That means I put an access point up here that covers a specific area, and then I can have multiple devices connecting back to this device. I probably would not use this specific nano beam in that situation. There's other models of radio that are more designed for that. We'll talk about that a little bit in the slides. But that's what I would do if I had my data center here, put some access points up on the top, and then connect multiple customers or multiple other connections back to each of those access points. Any questions on any of that so far? Cool. Okay, so going to try to breeze through. I think for me personally, it's helpful to understand, at least at a high level, kind of some of the terminology discussing wireless and RF so that we're all kind of speaking the same language. So I'm going to run through that quickly, and then we'll get into more how to plan these networks and how to build them and how to troubleshoot them. And I think we have until 1:45, right? I can kind of keep track.
2:45.
2:45, right, okay.
Yeah, 2:45.
Okay, cool.
Give some time.
Cool, okay. Where is my pointer? There we go. Okay, so RF stands for radio frequency. RF is part of The electromagnetic spectrum, visible light is also part of the electromagnetic spectrum, and other things like X-rays and gamma rays and things that we've heard of. And it's measured in, we're going to talk about some of the ways we measure and talk about radio frequency. Frequency just means how often something happens per second. So this little graph explains it nicely. The RF wave, one of its properties is how often it oscillates per second, and that's measured in hertz, abbreviated Hz. We'll get to the end of that. Wavelength is another, basically just another way to measure hertz, which is really just the distance between the peaks of the wave. We'll hear that commonly, but it's just another way of measuring an RF signal. And the wavelength of the signal is correlated with the size of the antennas. So there's some relationship there. If you kind of understand that and then look at the antenna, there's a relationship. The wavelengths that we're mostly talking about, most wireless internet networks today are built primarily using frequency in this range, 5,800 megahertz. Megahertz meaning millions of times per second. This is also described as 5.8 gigahertz, 5.8 billions of times per second. The reason is that there's a chunk of spectrum around this area that's been set aside by the FCC and other governing bodies to be open to use for this kind of thing with few regulations. So we can, I can put one of these up on my roof or up on a tower. I don't have to tell the FCC that I'm doing that. I don't have to buy a license. As long as I'm operating within the specs that this thing has and I'm not adding an amplifier to it or something, I can just use that without any extra permission from the FCC, or for the most part, similarly in outside the US with other countries' governing bodies in those similar bands. So that's why this band is so useful and so commonly used. Some of these others have similar properties and are also commonly used. 900 megahertz can be used that way. 2.4, which is kind of the original Wi-Fi band, can be used that way. And recently there's been a lot of work in the 60 gigahertz band, which also is similarly licensed or unlicensed and easy to use. And each of these have some different properties that can be used differently. Questions so far?
So, and I'll also ask Deborah for some of her experience with this. But so if you're going long distances, right, the 2.4 is better, from what I understand.
From a strictly RF perspective, yes. Yeah, from strictly just the way the radio frequency transmits through the air, the lower frequencies will go farther. There's a couple of other things that come into play there, though. One of them is that 2.4 and 900 tend to be a lot noisier. There's a lot of other stuff operating in those bands. And so even though the signal propagates farther, there's a lot of other noise, and that might make it just as hard or even harder to get that link to work well as if you were just using the 5 gigahertz.
Okay. If you were in an environment where you didn't have that kind of density of other connected, whatever it is that you're using that, if you didn't have that kind of a density, you would go with the 2.4?
Yes. The one other catch, though, is that there's a lot more spectrum available in the 5.8 gigahertz band. And with more spectrum, you can get more throughput. So if you, depending on how much throughput you're trying to get, you might even still be able to get more throughput at the same distance with a 5.8 gigahertz link versus similar 2.4 gigahertz link. So there's some other things to go into play there, but it is true that if you're strictly going for distance, you don't have a lot of noise, and you don't have really high throughput requirements, 2.4 is probably going to be better.
And when you say, where would you cap that? When you say high throughput requirements, what are you thinking?
So a 2.4 gigahertz link, if you don't have a lot of other noise, let's see. I'm trying to think of what products are available on the market right now. If you need more than about a few dozen megabits or maybe 100 megabits, you're probably going to be looking at more like a 5.8 gigahertz link. Depends on your situation, but probably.
You know,
Good question.
Kind of backhaul in a rural environment.
Yeah.
For the long distance.
Yeah, you know, how long distances?
Let's say, I don't know, miles, let's say 10, 15 miles.
Even at 10 or 15 miles, even just because of the products that are available, 5.8 is probably still going to end up being what you use. Just because there's a lot more products available, a lot more spectrum available. But you know, you can check out what's available and see what works for you.
What's the 60 used for?
60 is used for really, really short links. So the interesting thing about 60 gigahertz is that it has a very, very short propagation, which in some cases is obviously a downside, but in a lot of cases is actually an upside. The reason is once you start getting really dense deployments, like inside of a city or a dense suburb, you will become your own worst enemy. You will become your own worst interferer. So each of your customers adds interference to the neighborhood, and you are dealing with all of that and have to make all of these links work. So the problem with 900 megahertz is it goes forever. And so you can be 10 miles that way with your tower, and it's interfering with your tower over here because it just goes through the trees and goes through everything. So the great thing about 60 has this interesting property where it's right at a wavelength that the air really interferes with it. It's called oxygen absorption. And so 60 gigahertz has much lower propagation distance than even 70 gigahertz, which is also open for use in this band. So if you're doing a really dense deployment inside of a city center or inside of a dense neighborhood and going just like a few hundred feet on each wireless link, 60 gigahertz is great because you can reuse it everywhere and they won't interfere with each other.
Do the nanobeams do that?
The nanobeams do not do 60 gigahertz. Ubiquiti, somebody correct me if I'm wrong, but I don't think Ubiquiti has a 60 gigahertz product yet. There are other, we mentioned earlier, MikroTik has a 60 gigahertz product called the Wireless Wire. It's a pretty great product. It's like $200, and it's a gigabit link that'll go up to like 200 meters or something.
The Ubiquiti is 20, they have a 24.
Yeah, Ubiquiti has a 24. Yeah, the AirFiber. Yep.
But that's strictly line of sight, right?
Yeah, strictly line of sight. Yep. 900 megahertz is the only one on here where you might consider non-line of sight shots, and it's only going to be really low bandwidth.
If I connected this antenna to my computer, what would I see? Would it just be like, would it be transparent to my wired network interface?
You would connect to it with your wireless just like you were connecting to Wi-Fi. So if you were going to try to connect directly to this thing, you would just see an SSID and you could connect to it.
Oh, okay, so it is USB.
Oh, I'm sorry. I thought you meant if you were connecting wirelessly to it. No, this has Ethernet coming out of it. And so you would connect Ethernet, and then it has...
It translates between Ethernet and 802.11.
Right, exactly. Yeah, that's a good point. The question is, you know, how do you connect to this, and how do you get throughput to it? So this acts as a wireless bridge. It takes Ethernet in one side, regular wired Ethernet, and bridges all of the data out the wireless interface. So data just goes back and forth.
I did want to add a note for Althea specific. These will be connected to the Althea router, and you won't connect them with the computer, except maybe when you're setting it up to configure it.
Right. Yeah. Yeah. In the Althea network, yeah, these act as just the only time you really connect to it is just to set it up and test it.
If you're in a hotel room and there's like free Wi-Fi like across the way or something, could you use something like that to point to it, like a directional antenna? Okay.
Yeah. Yeah, you could.
Yeah, when you set one of those up, you see like every hotspot on the list, like every hotspot.
Yeah.
Like
In that direction.
You gotta find the pair on the other side.
Yep. Yep, that's true. Moving along here, a few more terms. Amplitude also defines our RF wave, and it's basically the loudness of the wave is called the amplitude. It's how loud it is. We'll talk about the TX power in a minute too. And so we put all that together, and we get this this RF wave. The RF wave, it's an electromagnetic wave, and so it has a wave in two directions: the electrical one and the magnetic one that go in different ways. That doesn't really matter, other than just maybe it's interesting. But we put all that together, and we get the definition of our RF wave, which is how these signals are actually propagating together. Any other questions so far? Cool. Okay, so we're going to talk about quickly the dB measurement scale. So a lot of stuff that you talk about with RF networks and RF planning, a lot of the things that we talk about are measured in dB for various parts of the antenna and the equipment. dB stands for decibel. We can actually measure anything with dB. So I'm going to kind of explain how it works, and then we'll talk about some of the things that we use it for. We use dBs to measure stuff when we want to be able to talk about really, really big numbers and also really, really small numbers using just a small number of digits. So it's a logarithmic scale that lets us measure really, really big things and really, really small things without using massive long numbers. So I'm going to run through how it works quickly. The origin point is whenever you see 0 dB of something, that's the same as saying 1 of that same thing. So in our case, a lot of the time we are measuring milliwatts. So if I say 0 dBm, meaning 0 dB milliwatts, that is exactly equivalent to 1 milliwatt. Everybody on board with that? 0 dBm, 1 milliwatt. As I go up, every 3 dB I go up, I double the thing I'm measuring. 3 dBm goes from 1 milliwatt to 2 milliwatts. So it doubles. If I go up to 6, doubles again. 6 dBm is 4 milliwatts. As I keep going, it keeps doubling. 9 dBm is 8 milliwatts. 10 dBm, if I add 10 to the number of dBm, I multiply by 10 the number of milliwatts. It's basically just a different way of doing the same thing. So 0 dBm is 1 milliwatt. 10 dBm is 10 milliwatts. Okay?
Is 20 dB 20 something?
20 dB. Any guesses how many milliwatts is 20 dB?
Do we know linearly?
No.
No, 100, because
100. I heard a 100 over here. It is 100. So once we get to this point, they start to diverge a lot. 20 dBm is 100 milliwatts. 30 dBm is 1,000. That's right, 1,000. So you can see quickly, and the reason I like to point this out, 100 dBm is 10 billion. The reason I point this out is because when you're putting one of these links up and you're at the home here and you're aiming this thing at your tower or whatever it is on the other end, the number that you see in here that you're watching to make sure these things are aimed well is the received signal level. That's how loud this thing can hear its partner. And we measure that in dBm. It's helpful and important to remember that if you are aiming this thing and you have it at, say, negative 57, and you can spend an extra 5 minutes and get it to negative 54, that's double the power. It's twice as good. If you can even get it 1 dB, that's significant. So it's worth spending a few extra minutes. It's important to look at these things going down too. A lot of times we'll see negative dB numbers. That doesn't mean negative milliwatts, it just means less than 1 milliwatt. So if going from 0 to negative 3 cuts our milliwatts in half. Negative 3 dBm is half a milliwatt.
Is it helpful to everyone to realize that this is exponential?
Yeah.
Okay. I don't know if everyone realizes that's what is going on
Yeah.
here.
It's a logarithmic scale that just condenses the numbers into easier ones to see.
How many negative dB is 0 milliwatts?
Infinite. Trick question.
Do you have a plot of this?
I don't. It'd be good to have though, but I don't. I'm sure we could find it. Yeah, it's a linear, or not an exponential graph. Same thing as we keep going down. Negative 6 halves again. Negative 10 divides by 10, decimates. Negative 100 is a very, very small number.
So in the case where your both of your transmitter and receiver. So I guess transceivers are within a short distance and it's pretty high.
Mhm.
What happens in that scenario? Because you mentioned the way you make sure you have a perfect link or perfect line of sight is by looking at the dBs, right?
Yeah.
So what if your dB is extremely high, and do those equipment provide some type of power reduction?
Good
with
question.
them? Or at that point, do you just decide, okay, I'm just going to be at 5 dB and just operate at that power?
Good question. So I think your question has a couple parts here. Let me make sure I'm getting it right. One part is can the received signal be too loud, and is that a problem?
Yeah.
Right? And the other question is kind of what do you do in that case?
Yeah.
Good question. So let me start by saying a common scenario, like this radio, I think these will broadcast at 7 dB. Do you guys remember? I think it's around 7 dB. These things, that's how loud this one is talking. And the other side, even if you're only, say you're half a mile away, you might be receiving at like negative 40 dB. So if you look at this scale, 7 down to negative 40, that's a big difference. There's a lot, these things lose a lot of signal going over the air. That's okay, that's the way that they're designed to work. Negative 40 is actually pretty good. They're designed to work down to like maybe negative 80. They'll still connect at negative 80. It won't be a very solid connection, but they'll connect. That's kind of the range that they work at. So where it comes into your question, if I'm right here and I'm looking at this and I'm looking at its received signal level, if it's hotter than about negative 30, if it's louder than about negative 30, that's too loud, and the connection will actually start to suffer, which is I think part of your question. In fact, I have a slide about that at some point. But anyway, at that point, what you would want to do is turn the other side down so that this side isn't hearing it quite so loud. And you can do that. They can be turned all the way down to, I think, negative 4 dBm transmit power, which would let us, even at this distance, they should be able to talk without being too loud for each other. Does that answer your question?
Is it common for antennas like this one to regulate the power, to like limit power consumption or maybe interference?
Yeah, so these radios do have a feature that I think I have a slide on called automatic power control that will, you set a target, you say this is where I want my received signal level to be, and if it's louder than that, they'll turn themselves down until they hit that. They'll try to hit that. They'll try to operate at that. Not all radios have that, but Ubiquiti does have that feature, and a lot of radios have that feature. This is just kind of a quick visualization of that same thing. Piece of paper, 0.001 meters tall. Anybody recognize that building? Yeah, Burj Khalifa, yeah. 828 meters tall. If we tried to measure these in meters or centimeters, you can see that regardless of how we do it, it's hard to measure both of them in ways that are like compatible, right? But if we use dB, it gets a little bit easier. So it's just a little visualization of why dB is handy rather than just using milliwatts. Cool. Cool. Okay, everybody good with that? Move on to a little bit different topic. Okay, so let's quickly talk about a radio and its components. All of the different stuff that is inside here that is part of this network. So when I say radio, what I mean is the part of the device that is actually creating or receiving the RF signals. So the part that's actually modulating the data onto a radio frequency network. So in this case, you're seeing everything is contained inside this little unit.
These slides are available after.
They could be, yeah, yeah, yeah. I mean, they're being recorded, and I think that will be distributed.
Yeah. They're being recorded, but maybe we can also get your slides.
Sure.
As well.
Yeah. So what I'm describing here is all contained inside this unit. So we can't really see it as components inside this unit, but it's still in there somewhere. So So we'll get that. So we have a radio, that's what generates our signal. And when we say transmit power, what we're saying is how much power is this radio generating? How much energy is it generating and sending out on the wire? There is a cable in there. And that cable is important because it can introduce some loss, so it's important to keep it in mind. We probably don't have to worry about it too much, but there is a cable. And then there's what we call a driven element. And that's it's just going to be a little piece of metal in here. That's what actually sends out the signal onto the air. If you remember, these are probably driven elements. There's some metal in there, and that's where the signal actually exits and goes out into the room. The radio that generates the signal is inside, but these are the driven elements. This one has one built into it somewhere too, and this one has it built in. So those are component. Oh, and then there's also a reflector. The reflector. I wish we had a light beam or something. The reflector, you can think of satellite TV antenna. So the signal comes in, the big dish on the back of the satellite TV, the dish part is a reflector. It's not active, it's not powered at all, it's not generating any energy or even really receiving any energy. All it's doing is basically acting as a mirror to bounce that energy back into the element that receives the signal. So it's kind of a magnifying glass. It takes it in and focuses it in one direction. So most antennas, especially ones that we work with, including these ones, have some kind of a reflector inside of them that directs the energy in the direction that they want. So they're a little bit they're directional. This device is sending more energy straight forward than out the sides. And the reason it's doing that is because of the reflector that's built in. Questions on that? Cool.
Maybe some of the Ubiquity gear, the radio, is this like a separate piece and some of it's integrated? I don't know if you want.
Yeah, I think I think actually the next slide has a breakout of them, so we'll see that. This is the next quick thing I wanted to point out is that most modern wireless radios for this type of application, including these ones, will have at least 2 and sometimes more radios. That's called MIMO. Maybe you've heard of MIMO, multi-in, multiple out. That it's a way to increase the throughput on the link, and the way that they do it is by adding multiple antennas in different polarities, different directions, and then sending data across multiple polarities. We don't have to get too much into that, other than just basically to understand when you hear MIMO, what that means is that each device has multiple radios in it. The different radios are each transmitting and receiving separately, and that's a way to get more throughput across the channel.
Does one radio handle both 2.4 and 5?
With these radios, typically not. These are 5 gigahertz only radios. It would potentially be possible to make a radio that did, but you probably lose some efficiency that way, so usually they're a little more specific. Good question. Some real examples of radio and antenna components. This one I put on here, this is a pretty old style of antenna. I think was maybe a WiMAX antenna, but it's something I've had for a long time. But I put it on here because it shows separately the antenna, which is this panel on the back. It's a flat panel antenna. It has the cable, which is the other component that is important and introduces some loss into the scenario. And then it has the radio separate. I thought it was nice to see them all separated out. Here's another similar one. Again, a little bit hard to break down, but it's got the big reflector cable coming off the side back here and off the bottom. So this actually has 2, like in that last example, and then the radios are all inside this device here. And then Ubiquity one. I think this is what everyone was asking, but this is another Ubiquity product called a light beam. Ubiquity products are great. Everything comes in the box and they fit together nicely, and for a lot of ways are really great. This is the reflector. This in this particular situation, and everything else is built into this, and all this stuff is just for mounting it on the pole. Questions?
My question is more for the Althea team. I was just wondering if all of your hardware is outdoor rated. Do you guys look into that, or you just?
Yeah, we've mostly just been using Ubiquiti gear, like these light beams. You'll see the light beams in the pictures of Medellin. And so that's all our outdoor rated. I mean, the only thing that I probably have that's not is the little cantenna that we made.
Is directional gear preferable for mesh applications?
Good question. The question is directional gear preferable for mesh applications? I would say yes, but there might be situations where you would want something less directional. In general, directional gear will always give you a healthier wireless connection with less noise, less interference, and better throughput. The hard part about directional gear is that it's directional and you have to aim it, and you have to aim both sides at each other. So it can be harder to build in a mesh system where every time you add a node to the mesh, you then have to go back and aim stuff. But I would say is more performant when you do it that way.
So it's all about the compound chances of packet loss. Directional antennas have lower packet loss, and the more hops you can go without packet loss, the higher the throughput. So it's better to aim.
Yeah.
Yeah, there's stuff coming out that can aim electronically, like the wireless wires do that to some extent. But most of the cheapest, best stuff today, you still have to aim.
Yeah. So when there is gear similar to, like, I don't know, this Linksys router that's sitting on the desk. So this hardware, I can imagine it uses some phase-related tricks to to direct the where it's listening from.
Yeah.
But is it also worth it to apply something like this with like antenna arrays to mesh applications?
Yeah. So the question is, phased arrays, which are used in these kind of MIMO applications, is it useful to use that in building these larger networks? Is that right? Is that the question? Yeah. Yeah. The answer is yes. And actually, these radios have some of that built in. The wireless wires that we just mentioned have some of that built in. And so that's becoming more common, and newer radio hardware will certainly contain even more of that. Yeah, I think that's important. It's probably doesn't totally replace aiming, at least not yet, but certainly helps. Good question. Okay, TX power. We mentioned TX power a little bit when you're planning wireless networks and deciding how to hook up a customer or hook up a site to a site. One of the first things you'll look at is how loud do your radios need to talk to be able to hear each other. We call that TX power. And as we've already discussed, that's measured in dBm or decibel milliwatts. The FCC does set limits at how loud your equipment can talk. So these radios won't let you broadcast louder than the FCC limits, or if they're in another country, you set the country code and then it limits it that way. But whenever possible, we want to talk as quietly as possible so that we're not interfering with ourselves. But this is more just a terminology thing. TX power, if you hear that or see that, all that means is how loud is my antenna talking? How much energy is it sending out? Opposite of that, I think is the next slide, is RX power. Or there's a couple of different names for it. RSSI is one name we see a lot. Receive something, I don't remember. Yeah, receive signal strength indicator. There you go. RSSI is a word for it. Sometimes it's just called RX, or RSL, receive signal level. And what that means is how loud, if I'm here, that's how loud this radio can hear that radio. So this is the important number to watch when you're aiming to make sure that these devices are lined up. That's the number that you're going to be optimizing, and you want it as, it will usually be a negative number, and you want it as high or as close to 0 as possible. I'll skip that. Questions about that? Okay, cool. Okay, so Gain and so we talked a little bit about the reflectors that go on antennas. When an antenna focuses energy in that way, that's called gain. So we take our regular antenna without any reflector on it, and it broadcasts and receives in a certain way. We add a reflector on it, and that focuses the energy better. That's called adding gain to the system. If we have an antenna without any gain, literally zero gain, that's called an isotropic antenna. You can't actually, it's not actually physically possible to build one like that, but it's a mathematical theory that they exist. We can compare things to them. We can kind of imagine it being like the sun in that it broadcasts roughly equally in all directions. But then as we add gain, that focuses the energy coming out of that thing in one direction. I think, so another example with a light bulb. We have our antenna broadcasting out in all directions, but if we want our signal to just go more specifically in one direction, we can add like a mirror. And that's similar to with in the radios, adding a larger dish on the back to focus the energy in one direction. Yeah.
Why would we care about that? Because is the equipment come pre-configured, or are we able to change the size of the?
It does mostly come pre-configured, so it's a fair question. Why do we care about that is the question. The reason is so that when you're looking at the 5 different models that Ubiquiti offers and you're wondering which one to buy, you can look at the gain, because they'll tell you how much gain they have, and understand which one's better for your application. That's the reason. Because like these devices have pretty low gain. Ubiquiti has another one that has pretty similar performance properties, other than it has a bigger dish that's higher gain and might be better for some applications. So that's why. That makes sense? Yeah, there's a rocket dish that's a really big one. There's a light beam that's a smaller one, that's still sort of big. There's a variety of different sector antennas that have different amounts of gain.
Yeah, even this model comes in a couple different.
Yeah, even this, yeah.
Yeah, so the same model with different gains.
Mm-hmm. Yep.
So the only thing that springs to mind when I say, okay, when you say scenarios, is besides distance, what other, you said it sells 5 different models, works in different scenarios. Besides distance, what other scenario would this come?
Distance is probably the main one. The next one would be for point to multipoint. How big of an area is it going to cover? So if I say, you know, I'm putting a tower right here and I want to cover 90 degrees, then I have a variety of different options to cover that 90 degrees off the tower, or maybe only want to cover 60 degrees. I have a couple of different options for that. And it's always a trade-off between gain and distance versus degrees covered. So that's another, so it's basically, so that's the other scenario. Yeah. Yeah.
This is kind of related to the previous section, but do you happen to know why the FCC decided to make 2.4 available? Because it is I think it's roughly the frequency at which water resonates, and so that's, to me, intuitively, it seems that it is not preferable to use that frequency because water and water-based life forms absorb that.
Yeah, and you have stumbled on the reason why the FCC let everybody use it. And the reason is that it's in use in microwaves, which is because it's the resonant frequency of water, and so nobody wanted it. So the FCC, go ahead and use it, because nobody wants it.
Is that also why 60 is used for the oxygen absorption?
Yeah,
Okay.
that's also why nobody, yeah.
What's the 5.8?
5.8.
Double the resonant frequency of water, which is
Okay.
effectively the same.
Yeah. Yeah.
Harmonic theory of resonance.
Yeah. Good questions. I also had just an example with those flashlights that you twist and they get brighter but narrower versus broader and less bright. That's another example of gain that is maybe helpful in visualizing adding gain.
So I don't know if this is going to help anyone, but I once held this very cool metaphor of gain, which is basically a balloon which you can squeeze. So you have like a finite amount of balloon, but if you squeeze it from top and bottom, you can like shape it into reaching farther out, or maybe in some certain direction. So that's my my understanding of how this works. Maybe that helps.
Yeah, I think that's helpful. Yep. Some quick usage scenarios. We talked about this just a little bit back here, but these are towers. We've probably all seen towers that look like this driving down the freeway. These antennas up at the top, these are point-to-multipoint antennas. These are the type of antennas that your cell phone is connecting to probably right now. It's something that looks like that and has similar properties to an antenna like that. These types of antennas are designed, they're called sectors, and they're designed to cover kind of a pizza slice coming off the tower. Could be like 60 degrees, could be 90 degrees, could be 120 degrees. And they're designed to cover that whole section. And anything in that section, anybody's cell phone or whatever that connects is going to connect up to one of those. So for example, you see in here, it looks like there's 3 of these mounts hanging off the tower. Each of them might be designed to cover 120 degrees, giving full 360 degree coverage around the tower. So that's an example. Those are going to be not super high, but not super low gain. They're going to be kind of medium gain antennas.
What about the vertical?
Good question. The vertical, question is, so horizontally they cover a section. Vertically, what do they cover? Each antenna has somewhat different vertical properties. You can usually find it in the specs of the antenna. Something like this, a lot of times it's like 15 degrees or so vertically, and so they aim it to try to have that hit the ground where they want to cover. Yeah, that's a good question.
So it looks like there's 4 covering each like 120 degree sector. Why 4? Or like why more than 1?
Yeah, good question. The high level reason is capacity. So 1 isn't enough. Mechanically, how exactly that works, I don't know. It probably just depends on the tower and who engineered it. It could be that each one is covering a slightly different vertical chunk and splitting them up that way. It could be that they're just, probably more likely they're all covering the same chunk but on different frequencies. So they have blanket coverage on all frequencies in the band across all 4.
Is distance the only thing that gain tunes, or is there some sort of like penetration signal strength also?
Yeah, so gain adds signal strength. So you can use that however you'd like. If you are going to try to blast through some trees, which I don't suggest, but you're welcome to try it, then the more gain you can get, the better. Interestingly, so adding gain adds directionality to the signal, which means it goes farther. It also cuts out noise, because gain actually works in both directions. So if I add gain to my signal so that it's going all directly in that direction, that equally has the impact that I hear from specifically that direction more. Does that make sense? So the gain really works in both directions, both hearing and sending. And it also has the impact of if I hear more from that direction, then I hear less from over here. So in a noisy environment, the ideal thing to do is to use as high of gain antennas as you can. The reason is so that then you can turn down the transmit power on your radios as low as possible, so that you're emitting very little noise into the environment. And because you have high gain antennas, you're not taking noise from these other places. And so your radios can operate efficiently, even at really, really low transmit power.
So I have a question about planning, because I guess for us who are not just going to go and buy an equipment first, right, and then try them, and then discover, oh, I could have bought one that was, $1,000 or $500 cheaper and done the same thing. So how do we do planning? How do we decide if I want to provide services X distance away? What would be the ideal?
Let me see where I've got that. So as it happens, I have that right here. So to do that, you use what's called a link budget. You can do this mechanically. In fact, if you Google link budget planner, you'll get a bunch of different things showing you calculators to do it. The way that works is you take all the properties we've just talked about, the transmit power on one side, the receive power on the other side, the gain of each antenna, the the cable loss, if there's a cable involved. You add all that together. It also depends on the distance between the two, the frequency that you're using, and any other loss you might need to account for. Like if you're in a heavy rain area, you try to account for the rain. You add and subtract all that together, and that gives you your expected received signal level. Oh, and in fact, I think I have this links to a calculator, but I don't know if I can get to it. Oh, I'll have to pull that up later. But yeah, that gives you your expected received signal level. And then, yeah.
So on this, because it keeps coming up, rain, and we've talked about wet foliage, does the humidity play in, like the difference between like Salt Lake City and New Orleans? Would you get different broadcasts because you're at like 15% humidity consistently versus 80%?
Right. That's a good question. I don't think it does enough, except for maybe in really high bands that you have to account for it. But it certainly wouldn't hurt to account for it. It's probably like a dB or something off. So that's, but yeah, it's a good question. Yeah.
My question, the original question is, is there any tool that you're aware of that we can use for designing and planning, like something cheap, where you know someone can be at one end and I'm at another end, and then we can see how strong the signal is or so? Have you come across anything like that?
Yeah, and I think I meant to actually follow up with that. The antenna manufacturers will provide, in most cases, they'll provide a table that shows at this received signal level, you can expect to have this throughput rate. So Ubiquiti, for example, on their website and in the statistics for each radio, they have that published. So you can say, okay, I did my math. I know I should have a negative 67 received signal level, so I should expect this throughput rate. So that helps, I think, with what you're getting at. The other thing is, these will tell you when you're at one side and one at the other, you can log into them, and we're actually going to do an exercise on that in a little bit, and they show all of that information in here. So if you're actually there physically doing it, you can pretty easily get all the information. Does that answer your question?
And Ubiquiti has an actual descriptive tool where you can place the antennas, what you're using, distance, the height, to give you a theoretical.
Yeah.
Level.
And it's free.
And it's free. Yeah. I think it's called AirView.
Link.ubnt.com.
Yeah, AirView I think is their spectrum analyzer. Yeah, they're. Link.ubnt.com.
Yeah, just make sure to repeat the question.
Oh yeah, thanks.
Yeah,
Was there okay, same thing. Okay. The question for posterity is basically is there a free or inexpensive tool for link planning, right, and understanding ahead of time what kind of equipment you'll need so that you don't have to figure out when you're there, right?
On the previous slide, what was the difference between like the drum antennas versus the...
Oh yeah, let me get back to that. Okay, I skipped ahead on that. This slide, right? So we talked about these antennas. These drum antennas are going to be really, really high gain antennas. So this situation again is for typically point to multipoint. I'm putting my equipment at a tower or at a building or whatever, and I'm going to, multiple of my customers are going to connect back to that antenna. This type of antenna is a really high gain antenna. That's probably there's probably another one just like it on the other side, and they're pointed right at each other, and they're a point-to-point connection. And that connection, you really just want them to be as high gain as possible, because like I said, you want all of the energy from one going to the other, and as little as possible going anywhere else. So whenever you see those, that's probably what that is.
What do you think is the hardest thing to debug when to troubleshoot when setting up a wireless mesh?
The hardest thing is when the numbers say you should have X throughput and you have less than that, and you don't know why. And
yeah, you have to go through the whole stack in order to find it.
Yeah.
The drums probably aren't using like 8 to 11, right? They're like, what,
No, these I don't know what these are. I just pulled them examples off the internet. They're probably something that's licensed, FCC licensed. Yeah. but they're examples of, you know, high gain antenna. Same thing. Were there any other hands? Cool. Okay, let me see where we were. So I wanted to show this. This is a radiation pattern. I think this is for a Ubiquity product called the light beam. And what we're looking at here is a top-down view of the strength of the signal at different angles coming off of that antenna. So if you imagine we're looking down at an antenna like this, that big lobe off the front is straight off the front. That's where most of the energy is coming out. And then there's these little side things where some of the energy comes out, and then a little blip off the back. Most antennas that you'll look at, including all the Ubiquity products, have these published. Can be useful if you're trying to plan a really dense deployment and you want to make sure these things aren't stepping on each other. If you are in a sparse rural environment, you probably don't need to look at things in this level of detail. But if you are trying to get a really dense deployment, it's helpful to be able to look at this and see where all the energy is going, especially because things like these side lobes, this amount of energy coming right off the side, you might not expect that if you didn't look at the radiation pattern. The other reason that it's important is here. If you have two of these, I'm at this side and somebody's at that side and we're trying to aim at each other. Maybe we're a long distance from each other. We can't see each other, and this can be tricky. Getting these things aimed can be difficult. You have one person on either side. Sometimes you'll end up, the way that you aim this is by just moving a little bit back and forth at a time and watching the received signal level to see when it's at its loudest point, right? That's the way that you aim them. What can happen is you can end up in this situation where this one is aimed that way, and I'm supposed to be aimed at that one, and I'm stuck on this. This is called a side lobe, and I'm stuck on that. So any direction I go, it gets worse, but it's not aimed as well as it could be. And so this is something you have to watch for when aiming these big point-to-point links. It's best to do the link budget ahead of time so that you know what the received signal level should be on either end, so that you know when you actually have it right. Otherwise, you can end up operating on that side lobe, and it won't work as well as it could, and you may not even know.
So, gain is a little nice, and gain is all nice, but what we call careful in reality is probably packet loss. Could you give us the ballpark of what good packet loss looks like, what bad packet looks like?
Sure. Yeah, that's a good question, a good point. So in a lot of ways, these radios will abstract the packet loss away from you because they're doing stuff internally so that you're not going to see packet loss at like even layer 2 because
it's going to get like internal retries.
Yeah. Like that. So you may not see that. But what it will give you is these. So what happens is once these two are talking to each other at a pretty low level that they don't really expose very much, they will negotiate what's called MCS rates. And I'm sorry, repeat the question. Your question, what's a good level of packet loss and kind of how does that play into the link quality, right?
Yes.
Yeah, okay. So the way that this works is, again, once these two are connected, they will start negotiating their MCS rate. And what that means is how much data do these two devices believe that they can pass between each other reliably?
So it's roughly like when you don't understand someone and ask them to repeat slower?
Kind of, yeah. The way it works mechanically, I believe, is that they'll send a bunch of packets, and if they get X number in a row that all pass their CRC checks, they'll bump up the rate. And then if they get packet loss, basically they get one that that's mangled or doesn't pass its CRC check, then they bump down the MCS rate.
Like TCP. Yeah.
Similar to lots of other kind of discovery protocols.
Is there a way to turn that off, to turn off retries? Because this is something I've wanted to do a lot because we can handle this better that way.
I don't think that there is a supported front-end visible way to do that.
Just to address also Justin's question, this is actually not retries. It's actually how many distinct frequencies it's using to try to transmit the data.
Right, that's involved here as well. So, but the thing I was trying to drive at is, so each of these, let me back up a little bit, each of these rates represents a different level of throughput, and there's a lot that goes into the throughput. One of the things is how many of the antennas are being used. Another thing is how much spectrum is being used, 20 megahertz versus 40 megahertz. There's coding rate, which I think refers to some forward error correction. There's the modulation type, which is how the data is actually going out on the wire. And so these two things will try to negotiate as high as they can, to be able to have as high throughput as they can with low error rates. And so driving to your point, once these two things have come up and connected and maybe passed a little bit of data, they're going to settle in on an MCS rate where they're comfortable communicating. That MCS rate will report back to you what the data rate should be. And that is kind of, I think, the lowest level you can get without really breaking into the hardware that will tell you kind of in a roundabout way the loss. It's using loss to get to that rate.
I have a follow-up question to that. Do you know of maybe dumber hardware which would maybe translate Ethernet to Radial 211 1-to-1? I mean, so my use case, my intuition for this is that, for example, I'm running a bird cam somewhere in the forest and want to hold the image back to my home. But with streamed media, you generally don't really care about losing some of the footage. You care about real time, maybe.
Sure.
Yeah. So that's that.
Yeah. So the question is there a way to not have the radios try to be smarter than they should be and just throw the raw data at you, right? I don't know of a way to do that. My intuition is that if you went to just using UDP rather than TCP to throw the frames, that would get you pretty close. Doesn't quite get you there, but pretty close. But there could be another way. So the question is, once you've got your links set up, is it set it and forget it, or is there maintenance, like expected maintenance, but also probably unexpected maintenance you have to do down the line? Yeah, so there's certainly you want to be watching them and make sure their performance stays consistent. Some of the things that can come up, wind can come up and move it, right? You can get around that by trying to install it better so that it's stronger against the wind, but sometimes happens. A tree can grow up in the way. That happens. Or even a building can be built up in the way. So yeah, there's definitely things that happen and you have to go back and.
But it's not something that's as common as like, oh, I have to go up again. I mean, do this every day or every week.
Right. The only thing that might be like that, if you're in depending on the weather environment you're in, sometimes you'll want to go back like yearly and put some kind of water-phobic coating on it so that ice doesn't stick to it. But other than that, there's not much you can do.
I was going to ask, I didn't realize the frequency was that infrequent. I was wondering if there was a tool that would allow you, if you had several of, I mean, when you have 3, 4, 5 of them,
Yeah.
but when you get up into the 50, 100,
Yeah.
is there a tool that would allow you to see which
Yeah.
using?
Yeah. So I don't know that it integrates with Althea yet, but there are a number of tools. Ubiquiti, if you're using Ubiquiti equipment, they provide one called UNMS, Ubiquiti Network Management System. It's free, and it does a really good job of managing Ubiquiti equipment. There are a number of others, including several open source ones that can monitor any type of equipment. So yeah, there are.
Yeah, just a note on how that integrates with Althea. So yeah, right now we don't touch the lower layer stuff. We're handling the payments, governance, and routing in the networks. That's all kind of above that level. So you might want to use. If you have a tower with a bunch of clients you're on an Althea network, you might want to use something like that to manage them all.
I think the one question we had earlier is, can the routing actually be built to allow them to route through? But we can.
Oh, sorry. the routing will choose the best path at Althea.
I mean, to be able to get from like a central NMS to the device, is there routing built up that will actually allow that?
Not yet, but it shouldn't be too hard to. So it shouldn't be too hard to do something that would let the antennas get out to like Ubiquity's cloud antenna management service, and then you just go to Ubiquity's website and you see all your antennas.
Well, it's also it's supplying internet access, so you can get to any destination on the internet. So, which
Right,
includes
if you
management
put them on DHCP or something.
Yeah, yeah.
But yeah, we can get into that later. Yeah.
One more thing before we leave the aiming.
Yeah.
I noticed there was like dead zones in between the lobes on those
Yeah.
point-to-point.
Let me go back to that. This one?
Yeah. So I was wondering, with the sector antennas, like the multi-point ones, do they have the same kind of lobes?
Yeah.
Or-
Let's see, I think I have one here. Here you go.
Obviously not really.
So yeah, so this is an example of, this is a, so the question is the radiation pattern that I showed just a minute ago was for a point-to-point style high gain antenna, and it had dead zones in between. There's these lobes, and there's kind of dead zones in between the lobes. Question is, do commonly sector antennas have those same dead zones? Here's an example of one Ubiquity product that is designed to be a sector, and you can see it, to the extent that we trust their marketing material, which is these, they have pretty nice, clean radiation patterns. That isn't necessarily true for all antennas of this style. This antenna is also sometimes called a horn antenna. It's not very tall. It's about like that tall and about like that wide. The sector antennas that are taller and thin, they often do have a little bit more of the kind of lobes with not quite dead zones, but lower zones in between the lobes. Yeah, again, you can always see those from the manufacturer, and at least in this case, you can see that they're pretty clean.
So usually the aiming is done for the point-to-point.
Right. So I would have something like this on one end that I would need to aim carefully at the sector, but the sector would stay in one spot and is, you know, covering that whole area. Let me see if I have. What's here? This one I've got. Yeah, good question. Anything else about that before I jump on?
Oh yeah, I was wondering if you explained the azimuth and elevation in those graphs and what that means.
Oh yeah. Yeah, let me go back to it. This one, right? Yeah. Okay, so the question is, explain azimuth and elevation in these graphs. And that's a fair question. So we have four radiation patterns here. The difference is we have vertical and horizontal. That refers to the polarity, so that there are two antennas inside this device. One of them is vertically polarized, one of them is horizontally polarized. That gives us our MIMO. So we talked a little bit earlier, haven't gone into it too much, but there are two antennas. Both of them can broadcast and receive. One of them in the vertical plane, radio frequency and electromagnetic radiation are polarized, meaning that they can come in different polarized planes. We don't need to get too much into that other than just to say that a vertically polarized signal can carry data while the horizontal carries data as well, and they won't interfere with each other. So what we're looking at here on the top is the radiation, the azimuth radiation, azimuth meaning my direction around a circle, like this, is kind of my compass direction. And we have the vertical, we also have the elevation one, meaning up and down. So, so this one top left is what the radiation pattern looks like looking top down at this thing with the widest part of that lobe going right off the front. The one top right is what it looks like looking at it from the side, vertical. And then the bottom two are the same thing, but in the horizontal plane, the horizontal polarity. That's your question?
Yeah.
Anything else? Cool. Oops. Okay. I was going to show this quick. So we talked a little bit about rain fade. When we're planning networks, a lot of things to plan for, obviously. Trees, vegetation, all kinds of stuff. One of the things we plan for is rain fade. the way mathematically to plan for that is to look at a map like this that shows basically what's the worst storm, rainstorm you expect to see over, say, a 10-year period. And that's going to put us in a zone with millimeters per hour of rain here at the bottom. So we look here, we're in, what are we in the, I don't know what the white zone is. Yeah, that's weird. I don't know why it's not colored there. We're closest to the B zone, which is, yeah, right? Yeah.
It's the D zone right there, just white.
Oh, yeah, it's D. Yeah, you're right. Okay, good point. So D zone, we're at 19 millimeters an hour. And so if you use a link budget calculator, the Ubiquity one or any other, it will let you put in that rain fade number, and then it will account for that in your links. So it basically, what it's doing is saying, when it's raining that heavy, you'll have a predictable amount of dB loss in between your antennas. And so you want to make sure that you have that much fade margin so that when it is raining that heavily, you have enough room that your signal levels decrease, but the links don't go down and they stay up at a rate that you would like.
Is there a setting for that somewhere? Have you seen that? You just top off the power in terms of phase?
Yeah, it's really just it really just goes into the link budget when you're planning it, because once it's there, you can only broadcast as loud as the FCC lets you, and if the rain gives you more fade than you can deal with, then the link will go down. So the question is there a way to have it automatically turn up the power when the rain comes and the signal starts to fade, right? Is that your question? And these radios do support, these Ubiquity radios and a number of others do support that. It's called ATPC, Automatic Transmission Power Control, I think, or Automatic TX Power Control. The only catch is that it will only go as high as the FCC lets you. So you can't go above that, but it will at least turn itself down if it can, so that you're not spraying as much noise out in the environment, and then turn itself back up if the signal starts to fade, like because of a storm. Yeah, good question. Any other questions there?
Question on that.
Yeah.
That chart.
This chart?
Yes, that type of information, weather information and all that.
Mm-hmm.
Is this kind of I'm probably testing the boundaries of your knowledge here. But is it, this information is like widely available for most environments in the world, or so like if you go to, I mean, is it just kind of like weather information layered on each other, or what are we looking at? Do you have any idea?
Yeah, good question. The question I think is, where does this graph come from and what does it include? I think is kind of your question. And yeah, the answer is I don't have all the information about this graph. Curiously, every time I Google RF rain fade, this is the graph that comes up, exactly this one. So I don't know who made it or why it's only this one. Presumably, you could do some research for any area and find out what you'd be looking for is, give me the heaviest rainstorms over, say, the last 10 years, and I want to know the millimeters per hour of rain. Presumably, you could probably find that in publicly available weather data for any location you're curious about. But this seems to do a pretty good high-level job of just telling you roughly whether what type of area you're in. Good question.
So the day-to-day condition is going to change. It's not going to fit exactly. That's an average of the weather patterns based on the geography.
Yeah.
And you can see how like it. But you can see like in India, they have monsoon season, right? Monsoon season in India and also Japan. And so that there's corresponding color and wind speed or rain speed. And you see like the rainforest, the tropic region. So over over Brazil, over the Amazon rainforest, and over the Indonesia. So there's similar patterns there.
Mm-hmm.
But this is not.
Yeah. This is intended to indicate worst case, like 10-year worst case. Let me, for the benefit of the mic, and to answer that question, let me kind of try to summarize. So there's a couple of important points here. The question being, what happens if you go afoul of the FCC, right? And how can you avoid that? How does Althea deal with that? How should you as a provider deal with that, et cetera, right? Is that fair? So a couple of things. One, a little bit of backstory, but Ubiquity actually got in trouble with the FCC somewhat recently for allowing people to kind of accidentally or maybe sort of on purpose not obey FCC limitations. And so Ubiquiti and I think other similar providers as well have done a lot of work to make it really difficult to accidentally do that. In fact, you have to work pretty hard to get a radio in the US that will let you choose anything other than US. It's not really as easy as a fat finger, at least with Ubiquiti and with other ones that I've used as well. So it's, at least in the US and with the somewhat normal level of trying to stay on the right side of the line, it would be pretty difficult to really accidentally be broadcasting on a channel not allowed by the FCC. And similar with the power level, they pretty tightly regulate the power level and won't go over that. So if you're just literally just concerned about it accidentally happening, it's probably not going to happen. You really have to try to do that. So yeah, I guess that should answer your question.
At what point of so if I am to set up a wireless mesh, and well, I look at this map for my region, where do you think lies the point where I might want to start considering a wired deployment instead, because the cost might be too big?
Yeah, good question. So the question is, looking at basically environmental factors, at what point would I want to consider a wired network because wireless seems unfeasible? Is that your question? Yeah, and that's a good question. And I don't know that this map would necessarily be the deciding factor. Probably it's some combination of this plus none of the buildings can see each other because there's all trees or buildings or whatever. If you have very low line of sight availability from points to other points, and you also have high rain, at that point wireless starts maybe looking infeasible. Good question.
I got another one actually. In what cases would you might also want to consider passive repeaters instead of maybe some nodes in the middle of the forest or something like that?
Okay, so the question, at what point would you consider passive repeaters?
Like reflectors or something like that. Even not the dumbest kind of.
Right. So so a question about passive repeaters, and quickly, just to sketch out a passive repeater, what you mean is basically an antenna, a cable connecting to another antenna, and nothing, a signal comes in here, goes out here, and vice versa, but there's nothing here, right? Is that what you're referencing?
Yeah, that or something completely passive without power reason.
Yeah, that's what I'm trying to draw here. No power, no amplifiers.
Oh, okay. I didn't even know that was possible, but okay.
Oh.
Let's suppose that's that.
Okay. So I don't know. The problem is the limits by the FCC for transmit power. So in this situation, you've got a broadcaster over here as well, and a broadcaster over here as well. And in order to make it through this and actually work, I don't know. It does in theory work. You could in theory do this and it would work, but you have to be broadcasting pretty loudly at either side because this is going to add quite a bit of loss.
Okay, yeah, because there is something like that for ham radio. You get like a mountain range, you put some reflective material that will just bounce and bounce and to the other side of the building.
Yeah, that's essentially what this is.
Okay.
You just have to be, but it is going to add a certain amount of loss, and you'll have to deal with that. Good question. Okay, I'd like to get into. Let me get rid of that. I'd like to get into until 3. Okay, half an hour. Okay, cool. Well, the rest of the things I'd like to cover are basically like channel planning and deployment planning. So figuring out how to kind of cover a whole area without stepping on yourself too much, and then depending on how long that takes, we can get into like some troubleshooting and stuff. Any other questions so far before we kind of shift gears? Cool. Okay, let me make sure I'm on the right slide here. Okay, so we've talked a lot about a lot of different things, but the spectrum that's available for us to use and things like that. This is a pretty nice chart for North America that shows everything in the 5 gigahertz band and how it can be broken up. Excuse me. So 5 gigahertz band, sometimes you'll see it referred to as Uni 1, 2, and 3, like there along the top. And this from 5170 to 5835 megahertz is the spectrum that's the 5 gigahertz spectrum, basically. That's what we mean when we say 5 gigahertz or 5.8 gigahertz. And that's, again, probably the most commonly used chunk of spectrum for this type of network. So you can see that each of these represents a different way to break up this spectrum. So when you were connecting these radios to each other, one of the things we're going to do is decide how much spectrum we're going to give them to use to talk. 20 megahertz, 40, 80, or 160. So you can see these down the left. Less spectrum means we can have more of these talking in the same area without talking over each other. More means that they'll have more throughput, but we can't have as many of them. That's the trade-off. So I think that I think these ubiquity ones in point-to-point mode, they do support 80 megahertz, but they don't support 160, I don't think. And in point-to-multipoint mode, they support 20 and 40 as well. So you can see that at 20 megahertz, you can have a lot of access points up or links at each other without overlapping. I haven't counted them. I don't know how many there are, but there's quite a few along this row, right? 40 megahertz, that starts getting a little tighter. 80 megahertz, you can only have 6 or whatever without. And once you get to that point, you have to start doing a little more work to have them not interfere.
I'd just like to note this for the room. If you have two channels that are overlapping, it's better to put them on the same channel. So if you have channel 1 and channel 1 and channel 2 overlap with each other on 20 megahertz channels, you want to put both on channel 1, because when you put them both on channel 1, 802.11 is smart, and they'll both cede time to each other, and they won't interfere. If you have one on channel 1 and one on channel 2, they're going to interfere.
Yeah, that's true. Unless you're using AirMax. Yeah, I'll repeat it. Yeah, I will. So the point being made here, if we say channel 1, channel 2, channel 3, channel 4, channel 5, channel 6, which isn't quite right, but you would not want to put one on this channel and then have one like right in the middle. So it's half on here and half on here. If that's the situation that you're in, it's better to put both of those access points on this channel so that they're right on top of each other rather than having them partially on top of each other. And the reason is they will attempt to work with each other if they're on the same channel. Even if they're not both your access points, even if somebody else's access point is on that channel and your choices are slightly overlap or sit right on top of each other, it's better to sit right on top of each other.
What does it mean when you have like the width of a channel? Like your actual wave is going to be on one frequency, right?
So kind of. So you have to. It has to actually modulate data onto that wave, and the more data is modulated, the more that wave will vary in frequency. So if you have a 40 megahertz channel, that means you've got a lot of room to modulate data on it and let it take up that whole slice. Where if you have a smaller channel, it can't modulate as much data, but it won't interfere with channels beyond it. Does that make sense? Yeah. Okay, so keeping this chart in mind, we're going to move on to now, how do I want to light up my city, and I've got this tower and another intermediary point at these other places. How do I provide kind of blanket coverage throughout the area without interfering with myself? Okay, so this situation, right? If each one of these circles is a tower, and say I'm using 90-degree sectors at each tower, and I want to be able to cover this whole area. But as we saw in that last slide, if I'm using 40 megahertz channels, there's no way I'm going to have enough channels to put each of these on a unique channel. So at some point, I'm going to have to reuse some channels, right? Not only that, but I'm probably not the only person using the band in the area, so I'm going to have to contend with what other people are doing. So how do we do that? Yeah, there's a lot of different strategies. And that's one way to start it. Yeah.
How do you combat echoes? Because, well, I can imagine a situation where, for example, you have this, you have some surface that will reflect your own signals with a significant delay. So, effectively, your nodes are doing replay attacks on themselves. To avoid that.
I'm not quite sure I'm following your question. Are you asking if there's something that's like RF reflective that bounces the RF back directly, or something else?
Maybe to the recipient of your message, like another copy of what you sent arrives a little bit later because of a reflection that happens because of longer path.
Yeah, you're talking about multipath, which is, I believe what you're talking about is multipath, where part of the signal bounces off something and then hits a little bit later.
Sounds like it,
yeah. Yeah, that is a good question. So let's talk about it. So the question is, how do we deal with what's called multipath interference? And what that means is, if this is my broadcaster and this is the receiver, and this is sending out a signal, but say there's a building right here, and part of that signal hits here and bounces here. So far on track? Then this piece of signal is going to arrive slightly out of phase with this main one, because the time is a little bit different.
So this phenomenon is probably happening at different levels. You can get different phase, or maybe like a completely different instance of a signal that's being parsed by the receiving node.
Yeah, it could be that far removed.
What are the differences between the two? Or is there any different dynamics related to that?
Yeah. So in this, there's a couple things that go on with this. Let's see. One is that some MIMO solutions, multi in, multi out solutions, actually make use of multipath. We'll try to detect these alternate paths and use them for data to send data along alternate paths as well. So in some ways, this is used as a beneficial thing, particularly in indoor Wi-Fi, but it's attempted to be used in outdoor Wi-Fi, where the multipaths are used beneficially. So that's one thing, and that's because each side has multiple antennas. So one antenna can hear this multipath, while the other one hears the main one, and they can try to pull data out of both. Okay. So that's one situation. Another one that we'll get to in a minute is, as long as you keep the Fresnel zone clear, we'll talk about Fresnel, I have a slide on Fresnel zone we'll get to, then the Fresnel zone defines basically the area where, if you can keep it clear, the reflections shouldn't be so strong as to totally cancel out the signal on the other side. So watching the Fresnel zone, which we'll get to in a minute, is one way to combat that. Yeah, we'll get there. Okay, back to this. Okay, so again, looking at okay, we're planning a tower. We want to put some access points. We want to be able to cover the area around the tower. When I say tower, I mean it could be your house, it could be the library, it could be a school, it could be a grain silo, whatever it is. I'm using a tower as a catch-all term for that. And you're saying I want to be able to provide coverage to my community from this central location. And what I need to do is put access points up on that tower, and I want to make sure they're not interfering with each other to the extent that I can, and also that I can go out through the rest of my community as I expand and add more coverage that then doesn't interfere with itself. So the kind of easiest naive way to try to do that at a single tower is this. This is, we call this like ABCD channel planning, where each letter represents a non-overlapping channel, and we're just going to put 4 access points on our tower, each of them on different channels, and they won't interfere with each other. This works okay for small and somewhat sparse deployments. where the towers won't be stepping on top of each other a lot. And if you're in that situation in a rural area, this is a great and easy way to start. Just put each access point on the tower on a different channel. But moving beyond that, if you need a little bit more density, there's some other things we can do. This is called an AB-AB channel plan, where what that means is that you put antennas that are back to back on the same channel. So if you have 4 antennas, you use 2 channels. The back-to-back ones use a different channel. The risk here is that if you remember from our radiation patterns, there is some radiation that comes off the back of the sectors. And in some cases, when these are back-to-back, that's coming off the back is enough to interfere with the customers of the access point pointed the other way. There's a couple of ways to combat that. One is to just use better antennas. The number there is the front to back ratio. That's the number you look for. That's basically the ratio between how much energy is coming off the front of the antenna versus how much is coming off the back. An antenna with a really good front to back ratio will work better in this deployment than one with a worse front to back ratio. The other thing we can do is what's called GPS timing. GPS timing is a really helpful tool. It's not part of the Wi-Fi spec, but we're going to talk about how it works because it can be really helpful as you're starting to deploy more dense networks. So the way that works is in this scenario, or using our antenna here again, if I have one thing we haven't really touched on is that these radios are half duplex. They can only either be talking or listening at once. They're never doing both. So when this radio is talking, that one's listening, and vice versa. With regular Wi-Fi that our devices use, the way that the devices decide who talks when is by using what's called contention. Contention means it's kind of similar to the way that humans interact in a group. What it means is that the first thing that this one does is listens briefly. If it doesn't hear anyone talking on its channel, it'll go ahead and talk. If it does hear someone talking on its channel, it'll wait a random amount of time, and then it'll check again, and then try to talk again. The nice thing about contention is that everybody gets to share the channel. That's how, when we talked about putting antennas on the same channel so that they will share the bandwidth, that's how that works. When anybody using that same channel goes to talk, they'll listen first, and if they hear anybody on the channel, even if it's somebody on a different access point, somebody they know nothing about, if they can hear them, they won't talk. If they can't, they'll go ahead and talk. So that's contention. That's how it works. It works really well, especially in indoor deployments. But for us in outdoor deployments, sometimes we want something different, so we use what's called GPS timing. The way that GPS timing works is that each device, and I don't know if these ones do, but the devices that can do GPS timing have a GPS chip inside them. They can get a GPS sync. Part of the GPS signal includes a very, very accurate timing pulse at a very, very, very accurate and like a beat that's very accurate. So what they can do is time each other's broadcasts. So when two devices are GPS synced, they can say, I'm going to talk in the on beats, you're going to talk on the off beats. We're never going to talk at the same time, right? We can even do that with point-to-multipoint. So this is an access point, and I've got multiple devices out there. My access points can say, you talk on beat 1, U2, U2, 3, U4, etc., and then none of the devices ever talk at the same time. What that means is, say I have 4 access points coming off of this thing, 1, 2, 3, 4. If all of them are GPS timed together, they're all going to talk at the same time. Then they're all going to shut up and listen at the same time. Talk, listen, talk, listen, talk, listen. The reason that works is that that means that the devices they're talking to are all listening at the same time and all talking at the same time. So what that means is that my device over here that's trying to listen to this, when it, I'm sorry, let me back up. What that means is that when this device that's aiming this way is trying to listen for its clients that might be way out there a ways and their signal level might be low, when it's trying to listen, this one is quiet. So these two pointing opposite directions from each other won't ever hear each other, or because they won't ever, one of them won't be talking while the other one's listening. Does that make sense? Am I making sense? Okay.
Maybe someone far away, right? You don't want
Right.
someone next to you talking.
Yeah, so it's like, you know, I'm trying to yell at somebody that way, and somebody's standing at my back trying to yell the other way. We both yell at the same time, and then we both listen at the same time, so that this person isn't yelling while I'm trying to listen over here. Make sense?
Sorry, just a question about just negotiation phase of
Yeah.
when someone talks and when someone listens with this GPS timing process.
Mm-hmm.
Who is there like some sort of master, or how is this? Is there a consensus algorithm that's used to decide that?
Kind of. So the question is, using GPS timing, we decide who talks when, and how is that decided, right? The way that that's decided is based on what we call our duty cycle, and a few other little factors. So what that means is when you don't use GPS timing, you don't have to tell the access point how much room to reserve for download versus upload. The access point can figure that on its own and just do it as needed. So the downside of GPS timing is that we have to set a specified percentage that will be reserved for download versus upload on the access point. So when you set GPS timing, you'll tell it, okay, I want to use 80% of my airtime for download toward the customer and 20% for upload. And then as long as all of the access points are set the same way, they will all use the same, so you know, if you have them all set to 80-20, then they'll all use the same slots for download versus upload. Does that answer your question? So the other downside that may have brought up is that, again, all of the GPS timing implementations are specific to the device manufacturer. So Ubiquiti has its own GPS timing implementation that does not work with Mimosa, that does not work with Cambium, that does not work with MikroTik. So if you're trying to co-locate all those different ones, GPS timing won't help you. Do you have a question? Oh, I thought you raised your hand.
Just jumping all the way back to the beginning. So in a 4 antenna scenario, then the two that are back to each other, you have them on the same channel. That's what you're saying.
Right. Yeah, and bringing the GPS timing into it. This ABAB, where you use 2 channels per tower, will work a lot better if you do the GPS timing. If you don't do GPS timing, this might not work very well for you. Yeah, because the antennas will be talking over each other. If you implement GPS timing, this will work well.
Have you used the prisms for sector prisms? I know they have a GPS.
Yeah, they have the external GPS antenna. Yeah, and that's what that's for.
That is what it's used for.
Yep.
Okay.
Yep. Mm-hmm. Yeah. Yep. Another implementation that works, again, better if you're using GPS timing. This is for 60-degree antennas, which is somewhat common. So you would put 6 up around the tower. That gives you 360-degree coverage. You would use 3 channels. We call that ABC channel planning. And again, back-to-back antennas use the same channel. So you can do, the reason that you might use 6 instead of 4 is all about capacity. Each one of these antennas, the Ubiquiti ones, recently I've noticed the customers will kind of start to slow down and get not quite full speeds at about 10 to 15 customers per access point. And at somewhere around 30 or 40, it gets pretty noticeable during peak times. The speeds slow down quite a lot. So if you put 4 access points on there and the customers are roughly evenly distributed, you could expect to hook maybe 50 to maybe 100 customers around on that tower without severe degradation. If you need to be able to do more than that, then you can start looking at like 6 access point deployments. 10 minutes? Okay. Cool. Let me see if there's anything else I really wanted to hit. Oh, let's run through this. I think I got 2 more slides, and then we'll just open up to questions. Fresnel zone, this is pretty important. We talked about this a little bit. So we've talked a lot, so consider these are buildings, and we are trying to connect them together. We've talked a lot about line of sight, that these things need to be able to physically see each other. There can't be anything in the way. no trees, no buildings, no mountains, etc. Fresnel zone describes an area around that line of sight that needs to also be clear in order to get a strong signal between the 2 points. So that green shape indicates the Fresnel zone. So not only do I need to be able to see it, but I need to have some clear path around it.
The shape of the radio frequency, the radio waves, or
actually, I'm going to show why here right now. So the reason, I kind of tried to draw it up here. The reason is that if there's something in the way, the risk is that part of the signal bounces off of that thing and arrives out of phase on the other end. What out of phase means is we have our main signal, right? Our wireless signal. And if a part of that signal comes in like this, they end up canceling each other out. And the signal gets degrades. That's called multipath interference. We don't need to worry about that too much. We can pretty much just track this. Say, as long as my Fresnel zone is clear, I'm probably okay. You can calculate the Fresnel zone. Let me pull this calculator up. Actually, it's kind of handy to see. Maybe I'll pull that up later. But if you just search Fresnel zone calculator, you'll get a plethora of them. The things that go into it are the distance between the links, the frequency, and that's it. The distance and the frequency. The distance and the frequency. And for 5 gigahertz links at a half a mile, I think if I remember correctly, it's like 10 feet is the Fresnel zone. It is shaped like this, the green shape. So at the edges, you don't need much of any clearance around the path, but right in the middle is where you need the most. Some common scenarios where this happens: if you're trying to shoot across a neighborhood, and you're like on one house on one side of the neighborhood and on another house on the other side of the neighborhood, sometimes the Fresnel zone will clip down into the roofs like that.
Is it a horizontal as well? 360?
Yeah, 360. Yep.
I always see it drawn vertically, so.
Oh, yeah, it is all the way around, yeah.
Does it not have also to do with the reflective property of like the surface you're going over? Like if you're going over snow or water, do you need a bigger?
Yeah, that's a good question. There are multiple Fresnel zones that you can calculate, and there may be something like that if you wanted to really heavily optimize, you could. I've never seen it necessarily calculated separately based on the reflectivity, but maybe you might need to. I have seen weird situations where it snows and all of a sudden things are worse.
I was wondering, does frequency have anything to do with the size of the Fresnel zone?
Yeah, so when you do a Fresnel zone calculator, the two things that go in are the frequency and the distance. Higher frequency, smaller Fresnel zone; lower frequency, bigger Fresnel zone. 60 gigahertz has a very tiny Fresnel zone, another nice thing about it. 70 even smaller. 5 gigahertz, isn't too bad usually. So, so if you're planning a link, this is another thing you might want to look for. You look for a Fresnel zone calculator, double check. Again, like if you're shooting across rooftops, what you might want to do is get a little bit higher up off the rooftop to make sure the rooftops in between aren't in your Fresnel zone. Or if you're like trying to shoot right between two buildings or right next to a tree or something, you might consider moving one side to make sure that your Fresnel zone is clear. Questions about that?
Is there anything you can do from the radio perspective to minimize this if you can't help the obstruction?
Yeah, so the question is there anything from the radio perspective you can do to minimize this if you can't get rid of the obstruction? You could, and it might kind of help to try to go higher frequency at the top of the band. Or just broadcast louder.
60 gigahertz or something.
Yeah, or higher frequency. Yeah. Anything else?
Broadcast longer?
Oh, louder. If you're not already broadcasting as loud as you can try louder.
Why would that work?
Yeah.
Why would powering up the power, why would increasing power not, I guess, eliminate the interference that occurs from the
Good question.
different phase?
So the question is, why would raising the power not just kind of cancel itself out, right, with a different phase? And yeah, that's a question that I don't think I actually know the technical answer to. But what I will say is that the way that Fresnel zone interference manifests is just by a lower received signal level than would be expected with a path calculator. And raising the power on one side does end up directly raising the power on the other side.
So in practice, it just works.
Yeah. There probably is a real reason, and I just don't know it. So, yeah. Good question. Yeah, I just wanted to hit, sorry, I know we're getting close on time, but I think that this is important. So let me just get this one last thing. And that is DFS. So DFS is, in the US, when the FCC released, I think, the Uni 3 band, they only did it under conditions that the people using it abide by what's called DFS. So there are some weather broadcast stations that use some parts of that same band, of the 5 gigahertz band. So any device like a Ubiquiti radio or any other device that uses that part of the band has to do with DFS. The way that works is the devices have to consistently listen for signatures of this radar starting up. If they hear the radar starting up, they have to drop off the channel, and they have to listen. So they have to immediately drop off the channel if they hear the radar, and you can't broadcast on any channel in that section unless you first listened for 60 seconds to make sure that there is no radar going on at that time. So in practice, what that means is two things. One, when you plug your radio in, it can't broadcast for 60 seconds. Two, what it means is that if your radio hears the radar, it will drop off and will most likely be off for 60 seconds until it comes back on. A couple of practical things here. One is that there are pretty well-defined areas where this is an issue, near airports and military installations, where you kind of need to plan ahead for this. The problem is that the detection algorithms are not perfect. Most of the detections that I've seen are false detections. They are picking up a reflection or something else that isn't actually radar, but the radio has to err on the side of caution, think that it is, and switch off the channel. So that's a problem. There are parts of the band, the lower and very top parts, or I guess now just the top parts of the band, that don't have to abide by DFS. So in a situation where you know this is going to be a problem, if you are in an area where this happens a lot, you can try to only broadcast in those channels. The downside is that those are already the most heavily used parts of the band. So there's already a lot of noise in there. So it's a trade-off to use them. So it's, I think anything Uni 1 and Uni 2 has to do DFS. Is that?
Yeah, just so you can see where the
Yeah.
It says right there.
Well, this is part of where they actually broadcast, but anything from here to here, you have to be listening for it.
Yeah, right there. He says this.
It's only up here that you can not have to abide by DFS. Anything along here you have to do.
It's so empty in that space too.
Yeah, so that's the nicest part of the band to use. It's the least used by other stuff, but you have to abide by this. In practice, the detection algorithms have gotten a lot better. So in recent years, I haven't seen it be as much of a problem. Still sucks to drop your customers for 60 seconds at random times that you don't have control over. One kind of cool feature that Ubiquiti doesn't have, but other companies like I think Mimosa have, is they actually have a second dedicated radio listening all the time and clearing a channel consistently, so that if they do take a DFS hit, they can swap to that new channel immediately. That's a cool feature. And it'd be cool if Ubiquiti added that as well. But yeah, it is what it is. So, questions?
Do you have any idea what the approximate distance from being from like an airport or something would trigger DFS all the time?
Not exactly. And it depends on if you're pointing at it or away from it or side. So I'm not even sure exactly which airports use it. So you'd have to do a little more research on your area to figure it out. you have a question?
Go ahead, Kevin. Okay.
Yeah, this is probably somewhat of a cynical question. And with a different audience, they will understand it. But here goes. What would the likelihood if someone wanted to disrupt your signal? So you come into some place and someone is unhappy. Is the likelihood of is that a feasible thing for someone to do easily, or
To try to force your radios to do this? Is that what you're asking?
Yeah, just interference, period.
Interference at all? Yeah, somebody could do that.
Anything you can do about it.
Not really. Yeah, I mean, if somebody really wanted to just generate 5 gigahertz signals really loudly for no purpose, just to mess with your network, there's not a whole lot you could do about it. The FCC might offer some recourse if it really was strictly malevolent, but I mean,
You should be able to track such a signal.
yeah, you could probably try to find it with spectrum analyzers and things.
But so if everything, and you would know when something like that is present. Yeah.
Yeah, these radios do have built-in spectrum analyzers. You would be able to get into them and run the spectrum analyzer and see a lot of noise in places where you maybe didn't expect it. Yeah, good question.
Go ahead.
Oh.
Are these the finest granularity channels that you can transmit and receive on?
I think technically you can go smaller, but it gets to pretty unusable bandwidth rates. Even at 20 megahertz, it doesn't give you a lot of throughput.
Supports lower than 20. If you tell a driver to do less than 20, it'll just say nope.
Yeah.
You really want to go up as high as possible, 40 to 80.
Yeah, you get a lot more throughput. Going 40 to 80. Yeah, I think so.
Out of the box, everything's 80 on 5 gigahertz these days.
Yeah.
Well, I mean, they do randomly adjust. You can set it to auto adjust. The high is a good 40 instead with ubiquity.
Yeah.
So most of them are 20, 40 base.
Yeah, I think point-to-multipoint ubiquity will only do 40. I don't think they'll do 80. They'll only do 40.
Right, just got 20, 40.
20 and 40, yeah. Right, yeah. Okay, should we move on?